Hello, I'm Jonathan, and today I'm going to be presenting some research on the Bloom filter performance for networking applications, in particular, basically Bloom filter implementation of packet filter for mitigating DDoS attacks. The project pretty much involves just benchmarking a Rust-based simulation to compare the performance of Bloom filters against traditional data structures such as hash sets in terms of memory usage, insertion speed, and false positive rate. So project overview. The overarching goal of the project was to explore whether Bloom filters, which are a space-efficient probabilistic data structure, I actually did a different video on how Bloom filters actually work for my RS4, so if you want to learn more about that, you can watch that video. And basically, I'm researching how Bloom filters outperform hash sets in certain scenarios that don't require perfect accuracy. In particular, we want to focus on DDoS mitigation, where we're more concerned about high throughput and memory efficiency than 100% accuracy. So my approach involved implementing both Bloom filters and hash sets in a packet filter simulation, and then benchmarking their performance under load, and then tracking the behavior under various configurations and data sizes. So initial goals. When I started the project, I had a few goals that changed throughout the course of my work. First, I needed to simulate high volume DDoS traffic that would push the filtering system to its limits and to really test the performance of the Bloom filter versus the hash set. So to do this, I first implemented my own version of the Bloom filter from scratch, and I also just used the built-in Studio STD library from Rust for the hash set implementation, and we basically just wanted to benchmark false positive rates, throughput under stress, and the memory usage over time, which is kind of the main focus, as we'll see later on. As this is where basically Bloom filters usually perform a lot better than hash sets. So Bloom filter integration. So for the Bloom filter, I basically I started off with my own implementation, but realized I'd rather just use a crate or a library someone else built, just for better performance and just for some cleaner code and to save some time. So I ended up doing that. So yeah, basically it supports multi-hash functions to ensure even distribution, a bit size arraying based off like a desired false positive rate, and the ability to insert dynamically without expanding memory. So these features were pretty much essential for simulating real world conditions where traffic volumes and patterns vary. So the DDoS simulation setup. So to test filters, I basically just wrote a simulation in Rust to generate large volumes of traffic from both like malicious and actually good packets, or yeah, IPs, I guess. So each packet had a randomized IP, and some were flagged as malicious based off a predefined list. And the filtering system then processed this traffic using either the hash set or the Bloom filter, and then metrics such as processing time, throughput, false positives, and memory usage were logged for each run. And then we basically just had a head-to-head comparison of the Bloom filter and then hash set. And yeah, basically to run, I just had some command line parameters that I passed in when running each test. So early benchmarking results, basically when using 1 million packets or filtering 1 million packets, the Bloom filter completed processing in 0.06 seconds, achieving a throughput of 16 million packets per second. The issue is that it produced a false positive rate of 0.02%, which is, yeah, it's definitely higher than the hash set false positive rate, because obviously by definition it produces 0 false positives. So on the right here we have the results from the simulation, and the hash set produced very similar results in terms of runtime. So this is kind of the core analysis of this research project, is the memory profiling. So to understand the memory better, I used a tool called Heap Track, which I think is only for Linux, but it lets you trace allocations at runtime. So the expectations were to see that the Bloom filter would use a lot less memories than the hash set, but unfortunately that did not happen. The Bloom filter actually showed slightly more allocations, as we can see on the right, and they're pretty similar overall. So my hypothesis is overhead from IP representations or underlying library inefficiencies basically caused this discrepancy in the results. So basically after that I refactored the code to improve accuracy. So we basically just removed confounding variables and refactored the benchmarking code. I removed a lot of the packet lookup logic and focused purely on insertion benchmarks. And instead of storing IPs in memory then inserting, we basically generated IPs on the fly and inserted them directly, and then added some more CLI flags to basically choose between which test we wanted to run, hopefully leading to cleaner benchmarks. But as we can see here, the results were pretty much the same as before the refactoring. So yeah, results still didn't add up. The Bloom filter had basically 1 million entries and theoretically only needed 1.2 megabytes, but as we can see here, it used a lot more. So some possible explanations is the memory overhead is still dominated by a random IP generation. The Bloom filter implementation may not have been fully optimized, and basically the testing scale was too small, so I considered scaling it a bit more. So yeah, I came up with a new test method here. And basically what we did is we used scripted benchmarking tools, and I created two new Rust crates or Rust projects, each one with the pure insertion of a Bloom filter versus hash set without the extra overhead created from simulating the DDoS attack. And then I just tested the insertion time and the memory usage using 2 bash scripts. For memory usage, we used proc and basically monitored VMRSS and VM size, which are basically just memory usage while the program is running. Then we've just plotted the results and stored them in a CSV. Or we've stored them in a CSV and then plotted the results. So insertion time results. So as we can see here, the hash set outperformed the Bloom filter in terms of raw insertion time. So as we can see for the number of inserts here, at around 100K, which is like the first test we did, they perform somewhat similar. The hash set actually basically half the insertion time of Bloom filter. The exact numbers for these two dots here would be 1.47 and then 2.69 for the Bloom filter. So the Bloom filter took pretty much double the time as the hash set. And as we can kind of see, as the number of inserts goes on, this gap widens a bit, but pretty much stays near like double the time, or maybe 2.5 times the time it takes to insert all. So this would be, right here, this would be 5 million insertions. So at 5 million insertions, we can see the hash set took 81 milliseconds and the Bloom filter took 182. So yeah, just a bit more than double the speed. So the reason behind these results is that the Bloom filters must run multiple hash functions per insertion, and perform a bit more overhead in terms of the bit manipulations on such a large array when inserting these like millions of values. In contrast, the hash set typically performs a single hash and inserts the key into a more optimized internal structure. So this is basically the space-time trade-off that I talk a lot about in my other presentation on my RS4 paper. But basically, hash sets are faster for insertions and lookups, while Bloom filters save more memory. So memory usage results. So this is kind of what the main focus of the project is. So basically, yeah, as we can see here, this is the number of inserts. So here we got 2 million, and then down here we have like 100K. So at 100K insertions, the hash set basically took 3,244 kilobytes, while the Bloom filter only took 2,740. So that would be these two dots here. So the numbers are somewhat close by, although the Bloom filter definitely has a lot less memory usage. As we can see, there are spikes with the allocations for the hash set here. So if we go to like 1 million, the hash set required 20,428 kilobytes, while the Bloom filter only required 3,680. So the Bloom filter does not require more memory as the number of inserts scales, while the hash set requires drastically more, almost exponential growth compared to the number of insertions. As we go towards the 2 million mark, the hash set required 38,976 kilobytes, while the Bloom filter only required 4,932. So that'd be this number here, and that's a huge gap. So basically, yeah, as we can see, as the number of insertions increases, the Bloom filter steadily goes up a little bit, while the hash set grows almost exponentially here. So yeah, again, just shows that when handling a large amount of data in memory, and you just care about the lookups and verification if a value is in the set, it's more efficient to use a Bloom filter if you don't care about a really low false positive rate. So moving on, we also built a packet filter simulator. It was built on a client server, or built basically just using client server architecture. Essentially what we did is each client connects to a server and will send packets, which would contain like a simulated IP address, since you can really run two separate IPs on localhost. So each packet that the client would send to the server would contain a different IP address that would either be malicious or clean. And based off that, the server would use the Bloom filter implementation of a packet filter to filter those packets. So key insights. Basically, Bloom filters are significantly faster at, Bloom filters have a much more effective memory usage, while insertions are a lot faster with the hash set. As long as the false positive rate is manageable within the Bloom filter implementation, especially for applications such as packet filtering, it is much more efficient to go with the Bloom filter implementation. Although hash sets are still better if false positives cannot be tolerated at all. Ultimately, Bloom filters allow for a pretty powerful balance between speed and memory, and an ideal trade-off in many real-world network applications. So future work, there's still a lot more stuff we can learn for this project, so we can scale up the testing to 10 million or 100 million packets to really stress memory. We could also experiment with the false positive rate a little bit more, so we can go down to rates like 0.001% or lower, as well as scale it up if needed as well. And we can maybe try different and compare different Bloom filter libraries, or even write a minimal custom one ourselves, and maybe do that in like C or some other language. And finally, basically apply this work to more complex network simulations or live data sets. And then, yeah, evaluate filters in other scenarios, such as intrusion detection or spam blocking. Yeah, and that's it. So thank you for listening to my presentation.